Let's see more. Which question you want to do? You want me to do? Let's see number 8. Number 8, we want to see if this series is absolutely convergent, conditionally convergent, or divergent. But this is a positive term though. This is not negative term. Absolute of n factorial over 10 to the n is equals to this. In other words, the term is non-negative. Okay, so it's either convergent, which is absolutely convergent, is already positive, or divergent. Okay, now let's have some feeling. What is the limit of that term? N factorial over 100n is 1 over 100 times 2 of, actually, let me do it this way. It will be n over 100 times n minus 1 over 100 n minus 2 over 100 all the way to 2 over 100 1 over 100. Right? This will be bounded below, and I need you to be explicit when you show your work. This will be bounded below by n over 100, 1 over 100, 1 over 100, 1 over 100, 1 over 100. Right? Okay, which is bounded to, which is equal to n over 100 times 1 over 100 to the power of n minus 1. Right? Actually, I don't like to do it that way. I don't like to do it that way. Hold on. I don't want to do it that way. I want to do it this way. Sorry. I want to say that for n greater than 100, you will eventually have 100 over 100 times 99 over 100, so on and so forth down to this. Do you agree? Okay. Now, that is equal to n over 100, maybe rounded up. It's less than equals to, this guy here is more than 1. Right? Call that 1, 1, 1. And then 99 over 100 all the way down to 2 over 100, 1 over 100. But the thing is, this is constant. This part here is constant. That's 99 factorial over 100 to the 99. This is n over 100. This guy will converge to what? As n goes to infinity, As n goes to infinity, this will be infinity. Right?
Is the exponent for the 100, is it supposed to be 99?
99, thank you. Okay, so by comparison test, actually, yeah, by comparison test, then the sequence converges to infinity, right? Okay, basically it's not zero. Agree? It won't be zero. And by divergence test, if the terms not convergent to zero, then the series will be divergent. Okay, so this series is divergence, of course. I don't need to check if it is absolutely convergent or absolute or conditionally convergent. That's for number 8. Number 12. Consider this series sine 4n over 4 to the n. Solution. Notice that this series, even if I put absolute sign, this is less than equal to the series. Notice that on the top, sine of whatever, absolute sine of whatever will be less than 1, right? Less than or equals to 1, this is for the n. Agree? Okay. Uh, but, now since, not but, since this is, what kind of series is this? Geometric with r equals to absolute of r is, what is the ratio?
1/4.
1/4. Now that's less than 1. Then the series is geometric and convergent. Maybe I said this way. I'm sorry. I said this is convergent because by geometric r is 1/4, which is less than 1. By comparison test, actually, is it by comparison test? I want to argue that because this is convergent, that this is convergent. What test is that? You remember? That's comparison test, right?
Yeah, why not comparison test?
I kind of like confused that with comparison test for the sequence, but it is true. It's comparison test.
Okay.
Yeah, by comparison test, then this series, the absolute series of the absolute, is convergent. Therefore, the series without the absolute is is what?
Absolutely convergent.
Absolutely convergent. How about number 16? The series, I basically do multiple of 4 until you tell me to do other number. 3 minus cosine n over 2 to the 2 over 3 minus 2. Ooh, this one is hard. Solution. I want to say this is divergent. But maybe, no, it's not divergent. This is conditionally convergent. But why? Let's see. Notice that 3 minus cosine n over n to the 2 third minus 2 is less than equals to greater equals to, this is at least 2, right? But at most 4. Agree? To be safe, let me say for n greater equals to, should I make it 3 instead or 4? Make it 4, make it 8. I just try to make the denominator to be positive. Okay, so the first couple terms, I don't care. In other words, this sequence is eventually bounded below by 2 over something, and bounded above by something. Okay, so limit, oh, but it goes to 0 too. Left and right goes to 0. You know what? I know what to do. Okay. The series 3 minus cosine n. You really need to get used to massage this. It's greater equals to the series from 1 to 8, let's say. So the first 8 terms, I make them exactly the same. Okay, but then from the 9th term to infinity, I'll bound it below by 2 over that. Okay, now then I will show that this guy is divergent. Okay, I want to show that that guy is divergent. Why does it have 4 in the denominator instead of 2 on the first step? Oh, should be 2. My bad. Should be 2 there. Thank you. It's a typo. No, I didn't type it, so it's not a typo. Okay, now, but then this will give us a constant, right? Let's call that constant C. plus 2 times the series from 9 to infinity of 1 over n to the 2/3 minus 2. Right? Actually, I can say further that this is greater or equals to c plus 2 times from 9 to infinity of 1 over n to the 2/3. Right? Well, because n to the 2/3 minus 2 is less than n to the 2/3, so the reciprocal will change the order of inequality. Is that right? Okay, but this guy here is convergent or divergent. I actually don't need this part. And this 8 here, if you wonder why you get 8, I think 6 will work, 5 even work, but I choose 8 because 8 to the power of 2/3 is 4. Minus 2, then that's positive. I just want to make sure the denominator is positive such that this thing works. Now, the last step here, I mean, not the last step, the last part here, that's convergent divergent. That's divergent by P series. P equals to 2/3, which is less than 1. So, by comparison test, the series that we were dealing with is divergent because we can bound it below. That's number 16. How about number 20? The series from 1 to infinity increase 2 to the n over n to the n. I think this is absolutely convergent. Let's see. All I need to show, I actually just need to show that the series of the absolute terms, this will be 2 to the n over n to the n. Is it right? This is equal to, oh, that's the nth term. Ah, you know what? Okay, let me say, after this, then I notice something. After this, I notice something. This have nth power. This has n power. Let me use root test. You know what? This is my scratch word. Consider this my scratch word. As the terms have power of n, use root test to get rid of them. Okay, so consider the nth root of negative 2 to the n over n to the n, that is negative 2 over n, that's convergent to 0 as n goes to infinity, right? So by root test, root test, I think I need to use absolute sign. So I don't know this. Go back to my notes earlier. I forgot the absolute sign for the root test. I should have an absolute sign here. So by root test, this series is absolutely convergent. And this part here, just my scratch word. That's for number 20. Let's see number 24. The series from 1 to infinity of 2n factorial over n factorial squared. Ooh. I think this is divergent. By divergence test, because the limit of the terms is not 0, but let's see. Scratch word first then, okay? 2n factorial will start from 2n and then 2n minus 1, 2n minus 2, all the way down to n, and then n minus 1, n minus 2, down to 1. While the denominator, n factorial squared, that is n factorial times n factorial, right? So n minus 1, n minus 2, down to n plus 1, and then we have n minus 1, down this. So you see something cancel, right? You see something cancel. 2n over n, 2n minus 1 over n minus 1, 2n minus 2 over n minus 2, all the way down to n plus 1 over 1. Even if I say that, this is greater or equals to 2, this is greater than 1, this is greater than 1, all the way greater than 1. Right? So the limit of n goes to infinity of 2n factorial over n factorial being squared is greater equals to 2, which is not 0. Right? So later on by divergence theorem, this will be divergent. Okay, so I think I will just use that, copy paste that to be my actual work. It's quite detailed. So solution by divergence theorem. By the way, in calculus 3, divergence theorem refers to something else. By divergence theorem, then that series from 1 to infinity of 2n over n factorial being squared is divergent. Number 32. Number 28, I see is quite complicated. I'm lazy, I don't want to do that. Number 32. The series is defined by the series A sub n, where the first term is 1. The n plus first term is 4 plus cosine n over square root of n. Determine whether this series is convergent or divergent, or times A sub n. Is the series convergent or divergent? Solution. I think I can do ratio test, right? The ratio test will be 2 plus cosine n over square root of n. Right? This is less than equals to 3 over square root of n, which converges to 0 as n goes to infinity. Right? So this series is convergent. In fact, you can say it is absolutely convergent. Okay, suggested homework from here is, oh, sorry. So would A sub n be 1 in this case? A sub n be 1? No. It becomes 0, right? Yeah, it becomes 0. Suggested homework for this 11.6b. Number 1 to number, I think up to number 33 is good. 33, and think about number 37. But don't worry about that number 37 too much, because we will actually answer that later in 11.9, I think. In 11.9. But we can do that too, though. The hint is use ratio test. Use ratio test. number 37. Now let's go on to 11.7. Strategy for testing series. This is the summary of 11.2 to 11.6. This is summary for 11.2 to 11.6. It's like at the beginning of this semester, we learned a lot of techniques of integration. And somewhere in chapter 7, as I remember, we have technique of integrations, right, to summarize that. Now, this 11.6 basically the same case. Okay, so we summarize everything here. Let's see what we learned. We have divergence test. Divergence theorem, I think we called it, or divergence test. I'll call it divergence test. We have comparison tests. Limit comparison tests. Oh, we have P-series, geometric series, alternating series tests. There's one more test I missed. What's that? Before we have ratio test and root test. Absolute convergence. So one way to show that a series is convergent is to show that it is absolutely convergent. That's what I'm trying to say. Okay, there's one more test that I forget. Integral test. Okay, there are some series you can use more than one method. There are some series you need more than one method. So you do comparison, and then later on you have P-series, for example. Okay, we have number 2 to number 38. You tell me which question to work on. Choose maybe 8 questions. You don't tell me anything, then I will do something. I think I will do multiple of 4. Number 4. We have alternating series here. Okay, I think I saw this question earlier. Right? You remember this question?
Yeah, I think we did it.
Yeah, that's like n squared plus 4 at the bottom. And then we have n minus 1 on the alternator. Okay. Well, okay, you work it out yourself. But do you remember what was the conclusion here? Now, instead of remembering, can you tell what's that? That's alternating, similar to alternating harmonic series. Right? Which we know is conditionally convergent. But this is just instinct. Don't answer it that way in your test. Okay? I just give you a hint. Okay, this is similar to alternating harmonic series. and it is conditional convergent. Therefore, you need to show that it is alternating by alternating series test, it's convergent, yet the absolute, the series of the absolute term is divergent. Number 8. The series k equals to 1 to infinity of 2 to the k times k factorial big over k plus 2 factorial. Let me use ratio test. Ratio test a sub k plus 1 over a sub k. That is 2 to the k plus 1 times k plus 1 factorial over k plus 3 factorial times the reciprocal, right? K plus 2 factorial over 2 to the k factorial. I don't need the absolute sign. So I get 2, or this guy cancel this guy, give me this guy. Right? And then let me match this guy with this guy. Give you what? Give you k plus 1 on the top. Right? Over this guy with this guy give you what? K plus 3. Is it okay? So this is 2k plus 2 over k plus 3. Now, you know this will converge to 2, but you still need to show it properly. 2 plus 2 over k over 1 plus 3 over k, that is convergent to 2, which is greater than 1. So the series is divergent. Strange. I somehow thought that this would be convergent. I somehow thought this would be convergent. Wow. It's quite dangerous. I really thought that this would be convergent, but it's not. My bad. Yeah, it's not. That's number 8. How about number 12? What do you think? This is not alternating, so we don't worry about conditionally convergent. It's either convergent or divergent. Idea. Consider bk equals to 1 over k squared. Now I will perform limit comparison tests. So a sub k over b sub k equals to 1 over k square root of k squared plus 1 over 1 over k squared, that is equal to k squared over k square root of k squared plus 1, which is k over square root of k squared plus 1, divided by k. Actually, I can just divide by k squared earlier, huh? What am I doing? Thinking too hard. Divide by k squared, this guy divided by k, and then this guy divided by square root of k squared. That's 1 over square root of 1 plus over 1 over k squared. That's convergent to 1 over square root of 1 plus 0, that's 1. Which is greater than 0, right? Okay, so by actually I need to say first that bk is convergent. The series bk from 1 to infinity is 1 over k squared, the sum of 1 over k squared. This is convergent because by p series, that's right, by p series, and the p is what? P is 2 greater than 1. Okay? So the series that you compare to is convergent. Therefore, the series that you start with so by limit comparison test, by limit comparison test, this series, which series? You need to be explicit. 1 over k square root of k squared plus 1 is convergent, right? But that's the first solution. You know I work hard. The second method, the second solution, which I think is easier, this series here is less than equals to, maybe I'll say that this term, instead of the series, this term is less than equals to 1 over k squared for every k greater equals to 1. Is that right? So the series, see, I really work too hard. It's less than equals to this series. By p series p equals to 2 the series on the right-hand side that you bounded above with is convergent. And therefore, by comparison test, your series is the original series that you try to test is convergent. Okay. But let's say you need to also show that it is actually non-negative. Why can't you compare that to 1 over k? The thing is, why can you compare that to 1 over k? The thing is, you bound it above by something divergent doesn't mean that's divergent. This is true. But the thing is, this series is divergent doesn't mean the one below that is divergent, no. But you need to, if you want to bound it above, you bound it above by something convergent. If you want to bound it below by something divergent. Okay? The issue arises, I think I'm about to give you a break. I am about to give myself a break. What if what we have is the series k equals to 2 to infinity of 1 over k times square root of k squared minus 1. You see? At the first sight, my hint will be, this is similar to, it's similar but not bounded above by 1 over k squared. You want to bound it above by 1 over k squared, but it's not. That guy is greater than. That's greater equals to 1 over k squared. So you cannot bound it above. Okay, but because it behaves like 1 over k squared, it gives you a hint that you will do limit comparison test. Okay, now let me give you something else, another method. Notice that 1 over k square root of k squared minus 1 is less than equals to 1 over k times square root of k squared minus k. Can I do that? Right? And that is equals to 1 over k square root of k times square root of k minus 1. Notice that your k starts from 2. Right? Now notice that this is less than equals to, so I keep on doing squeeze that, compare that. This is k square root of k, which is 1 over k to the power of 3 half. This is convergent later on. This series is convergent by P series. Okay, so by comparison, this will be convergent. What I want to show you is this. You can use limit comparison test, but you can also find a term where this guy is greater than this guy, but yet still positive. Okay, now notice that then I can factor square root of k this guy is always greater or equals to 1. Right? So you can bound the whole thing now above by this. That's just another trick though. Okay. Your success rate in this chapter really depends on how much exposure you get into those techniques. You tell me number 16. Before I take a break, I really need a break. Honestly, I'm so sleepy right now. Do you think this is convergent or divergent? Do limit comparison test. With respect to what? Any idea? 1/n. Okay. Fast forward, you will get n cubed plus n over n cubed plus 1. Fast forward, this will converge to 1, which is greater than 0. Okay, and then the series, the way you show the work later on will give, you need to give me more details. Okay, now this series is divergent by harmonic. Or you can say it's harmonic, therefore it's divergent. Therefore, the original series that you're testing is divergent by linear comparison test. Okay, let me take a break. I come back at 8:50. That's number 16. Do you have any questions you would like me to work on? If no, then I just go on with multiple of 4. Number 20, the series from 1 to infinity, is it from 1? Yeah, that's from 1, of cube root of k minus 1 over k times square root of k plus 1. My hint is this term is positive, at least non-negative, and similar to k to the 1/3 over k times k to the 1/2. That's 1 over k to the power of k times k to the power of 1/6. K to the 7/6. So I think I will compare it with k to the 7, 1 over k to the 7/6. Actually, I don't need to. Actually, I don't need to. Actually, you see that the cube root of k minus 1 over k times square root of k plus 1. That's at least 0, but it's less than equals to cube root of k over k times square root of k, right? So on the top, you get greater. This guy is greater than this one. On the other hand, on the denominator, this guy is greater than that one, right? So no, I don't need to do limit comparison. I can just do comparison. This is equal to k to the power of 1/3 over k times k to the power of 1/2. That's 1 over k to the power of 7 over 6. Now then, we can talk about the series. This series is convergent by P series P equals to 7 over 6, which is greater than 1. So by comparison test, the original series that we talked about is convergent. Number 24. The series n times sine of 1 over n. N equals to 1. I think this guy here, this will go to 1. Let's see. My scratch word. So n sine 1 over n, that's equals to sine 1 over n over 1 over n. Right? Okay, if I use superposition function, then I will get sine 1 over x over 1 over x. Now that's for x goes to infinity, right? But when x goes to infinity, then 1 over x goes to what? Goes to 0 positive. Let's call that u goes to 0 positive of sine u over u. Okay, you can use L'Hopital rule, but I think from here, just remember definition from calculus 1, this is equals to 1. Right? Okay. Use that idea. Now, of course, you put that in more organized work, but eventually you will say by the Convergence test, the series is divergent. Yeah, because the limit is not 0. That's number 24. How about number 28? Hmm. e to the 1 over n squared, that's positive, non-negative, and it is bounded above by e over n squared, is that right? In other words, e to the 1 over n is less than e because e is less than e to the n. Is it right? Okay, that's the idea. Now notice that I bounded above. This is e times the sum from 1 to infinity of 1 over n squared. This series is convergent because my P series t equals to 3, which is greater than 1. So by comparison test, the series e to the 1 over n squared is convergent. Ooh, that's nice. I'm kind of a bit bored right now, so you try to think about this, number 36. Actually, how about number 34 first? The series n plus n cosine square n. I want to say that this actually at most 1, at least 0, right? So this will be bounded above by 1 over 2n, the series of 1 over 2n. That's what I want to say. Okay, the one I circle in blue here is the idea. Now don't do that in your test. In your test, you do such thing, the idea on your scratch paper. So cosine squared n is at least 0, at most 1. Now n times that will be at most n. Right? Multiply by n, and then plus n. Now then when you do the reciprocal, then this n plus n cosine squared n is greater equals to 1 over 2n. So the series is greater than the series of 1 over 2n, which is 1/2 harmonic series. Now you see I bound it below by something divergent, right? Which is harmonic. Therefore, divergent. So by comparison test, this series, again, every time you say you want to say this series, be explicit which series you're talking about. Is that version. How about number 36? They use ln2. 1 over natural log of n to the power of natural log of n. Interesting. How would you do this? Improve. Does the root test only work for powers of n? Most of the time. You want to try that here? Let's try that here. Use red color. So nth root of natural log of n to the power of natural log of n. This is natural log of n to the power of ln n over n. That one is difficult. Oh, you know what? And then this is equals to e to the ln of ln n to the power of ln n over n. I wonder if it helps. I guess not, huh? This is e to the ln n times natural log of n over n. When n goes to infinity, so I assume I use x, which is not appropriate because this is already with nth root. So this is when I do L'Hopital rule, this becomes 1, this is 1 over n, this is 1 over natural log of n times 1 over n. This eventually goes to 0 on the top, so it will eventually goes to 1. Inconclusive. Nah, not for this. I think let me try it in this way. Let me try natural log of n times natural log of n to the power of natural of n. This is e to the natural log of natural log of n to the power of natural log of n. Okay. This is e to the natural log of n times natural log of natural n. x is bounded above by e to the natural log of n times natural log of n. Oh, then this is e to the No clue, no clue. But I think I start seeing something. Natural log of n is less than equals to n. That one is true, right? Actually, this is true for every n. Now, therefore, natural log of n to the power of natural log of n would be less than equals to n to the power of natural log of n. The reciprocal, therefore, ah, 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 ah. Still doesn't help. Hold on, hold on, hold on, hold on. Eventually, that is. Nah, I don't know. I need help. Let's see. Let me try again. This guy is less than equal to n to the n. What if we compare to 1 over n? Very likely you're right. We start from 2, right? Start from 2. or actually that is not true though, because this may be greater. So h dot of n like this, n greater equal, or actually n greater equals to e, make it 3. So it's more than 1 already. For 2, ln2 may still be, it's positive but less than 1. So for 3, it will work. Now the thing is, if I do the reciprocal, I bound it above by something divergent, but it doesn't help. Hmm. I want to bound it above by something convergent or bound it below by something divergent. Hmm. I don't even know that. What if we compare to 1 over ln n, 1 over n? Using ln up, ln n to the power of ln n. Is it less than equals to n? If that's true, then the following is true. Hmm. Maybe the other way around, huh? For n, let's say greater equals to 3. Or e to the 3, maybe 27. But still, even if this is true, if this is true, then this is true, the reciprocal doesn't help. You see that we bound it above by something divergent, doesn't help. One over n less than 1 over n. Is it true? Is it true that 1 over n is less than equals to 1 over n to the power of n? No, it's not. It's not. I mean, you can use n equals to E. Oh, I mean, yeah, that one is true. Well, what I want to say, if that's true, it implies n is greater equals to ln n to the power of n. Is it true? If that's true, then this is true. I apply natural log to both sides. But apparently this is not true for some n. You see, you can cancel ln n, right? You know this is not true. Not true for n greater equals to, let's say, 0.7. So, no. Let me try again. Did you try root test? I think I tried that earlier. It didn't work well. At least it doesn't give me any good conclusion. Very short. So you try to do it instead of you tell me. You try that first. If it works, let me know. Hmm. What if we sub something for ln n and treat that as geometry? That's what I would like to. What? What would that be? I wonder if square root of x is square root of x greater than natural log of x. Is it true? That's how I try to shift from exponential or logarithm to radical. I don't know. I don't know if this is true. I can graph it to check, but you know what? How do I show? Maybe this is a secret. How do I show that the square root of x is greater than or equals to ln x for x greater equals to 2? How do I show that? Or greater equals to something. Let's call this fx. Uh, when x equals to 1, that's positive. Now I need to show that the first derivative after 1 is positive. So if x is increasing for x greater than 4, let's call it greater equals to 5. So square root of n is greater equals to ln n for n greater equals to 5. I wonder if it helps. Still doesn't help. I'm sorry. I have no clue for this. You know what? Let's try integrate this. Which I don't think it's doable, but no, it's not doable. Hmm. Nope. I give myself 10 more minutes to do this. If in, no, actually 5 more minutes to do this. If I have no clue, then I move on to the next section. But that becomes a big question for me too. I did this problem before, so I know I could do it. I just don't remember how to do it. Oh, I'm recording this. It's a waste of time. Okay. You know what? Let me do this. I kind of grief up a little bit, but I show you what I think I try to do. Let's do the comparison of y equals to ln x. Compare that with square root of this. Y equals to x square root. Oh, square root of x is always greater than. How about cube root of x? Oh, eventually it's below, right? Eventually it's below. Maybe that's what we need, huh? Yeah, maybe that's what we need. Okay, then go back to scratch code. So natural log of n is greater equals to the cube root of n for, let's say, n equals to e squared. Or maybe e cubed. Yeah, e cubed. Okay, how do I? So what? This is less than equals to 1 over n squared for n. What the heck? Okay, okay, I think I know what to do. Okay, I think I know what to do. So natural log of n is greater equals to cube root of n, which is n to the power of 1/3. So natural log of n to the power of natural log of n is greater equals to n 1/3 to the power of ln. But this is definitely greater than equals to n squared for n greater equals to e to the 6. Right? Okay, so now I think I know. So this is this series here. Maybe I'll do this one first. Natural log of n is greater equals to cube root of n for n greater equals to e cubed. And proof. So first ln e cubed, that's equals to 3. Cube root of e cubed is e. Clearly, it's greater, right? But that's only for 3 though, for e cubed though. I also need to show that for n greater than that. Multiply e x multiplied by square root cube root of x. Oh no, this is negative. I don't know. I don't know. I need to think about that. Somehow I would like to argue now that 1 over natural log of ln, this is less than equals to 1 over n to the 1/3 of ln. This is true for n greater equals to e cubed. And this is less than equals to 1 over n squared. That's for n greater equals to e to the 6. So this series is bounded above by that. And we know this is convergent, right? This is convergent. So this would be convergent. Now my argument seems to be okay until I am forced to prove a couple things. I need to prove that ln n is greater than equals to cube root of n. I need to prove this. Okay, now to prove that, I try to find this function. And I want to show that this is always positive. Okay, that's my issue. Well, anyway, suggested homework from this 11.7, number 1 to number 37, think about it. And on Wednesday, we will do 11.8, 11.9. Actually, 11.8 is quite easy to read. Please read that. And you will see a lot of them actually mechanical, quite mechanical. Okay, at least the basic one is mechanical. Now, 11.9 requires us to do plenty of work. Okay, so I will stop here. Now, trust me, I won't be able to sleep to think about this question number 36. Maybe if I get the idea somewhere in the middle of the night, then I will post the solutions in the announcement. Okay, that's for today.
Thank you. Good night.
Okay, bye-bye.